I will go ahead and share my screen with everybody. And I'm going to move things around here a little bit so we're good to go. And before we get going, I just want to check in to be sure that you guys can see my screen here and you can hear me. Yep, I got a yes. Everybody else, you can hear me? Okay, wonderful. All right, we're doing fluid power. All right. And we'll talk everybody about how we're doing with that in a minute. But same thing, we've got our review and our lecture, and then we'll take a quiz after this. So immediately after this, we'll take the quiz. And next time I see you, we do the fluid powered lab. So we're going to talk about the history of hydraulics and pneumatics. Do you guys know what hydraulics and pneumatics are? Just on a scale of like yes or no, or maybe, yes, no, maybe. Do you guys know what hydraulics and pneumatics are? Loosely, okay. Anybody else? Hydraulics, yes. Pneumatics, no. Interesting. All right. If you're in the METS anybody who's in METS program, you'll be taking a lot of METS class with hydraulics and pneumatics, but we'll review it. We're going to do cylinder types, valve types, and pneumatic applications. All right. But before we get that, we're going to start with our review. So we learned that a relay is an electrical switch. Okay. There are solid state relays that switch still with electricity, but no moving parts. And there are electromechanical relays. And that's what we were working on, was the electromechanical relay. You'll be exposed to electromechanical relays a lot in 131. So I'm going to grab one. Hang on. Here it is. So once again, this was my electromechanical relay. And we put voltage here to 17 and 18. And that caused it to click. Okay. And when the magnetic field pulls this down, it closes contacts and it opens some other contacts. So there's normally open and normally closed contacts on here, and the electricity, the magnetic field pulls this down. So it's almost like a push button, opening and closing, except a magnetic field does it. So on a scale of 1 to 10, do you understand that concept that electricity causes this to move and to switch instead of me pushing the button? Scale of 1 to 10, how do you feel about that? Pretty good about it? 10s? Yeah, a push button, I have to activate it. An electromechanical relay, it's electricity and a magnetic field. All right, and that's what you learn in 131. And once again, ours move, others don't. They have a coil that was, like I said, the 17 and 18s where we ran the electricity to cause it to switch. And then there's normally open and normally closed terminals. And the relay says, you know, what they are here. So it says, these are all my opens here. So I got 1 and 2, 5 and 6, 9 and 10, 13 and 14, and they're all marked here. So there's a lot of different ones that close, and some are closed and then they open, and all the opens are here: 3, 4, 7, 8, 11, 12, 15, 16. And once again, it indicates here 17 and 18 is a coil, and the coil is depicted by a coil of wires depicted by the round right there, and that's what we did on the lab. We drew that. Okay. So we said that relays are used for latching or for memory, and that was the one circuit that we did. And what we did is we had a stop button, and then we had that was normally closed. We had a start button that was normally open, and then we turned on a control relay, and then we used the contacts of the control relay. This is a 1CR, 1CR. We used the contacts of that control relay to hold itself on. So when I hit the start right here, and then I let go of the start, it turned itself on with a path of electricity. And then I had to hit the stop here to turn off the coil, 17 and 18, which would then open 1 and 2, and it would be dead again. So does everybody understand the memory circuit here? A scale of 1 to 10 of how it works. How do we feel about the way this memory circuit worked? So that was momentarily and it kept it on. Yeah, and those that are doing the 131 will see it. All right, hit the start and it goes. Another thing a relay is used for is isolation. So you could have over here, you could have the coil of wire over here on this circuit right here, and then you put voltage to it. You get a magnetic field right here. This coil of wire makes a magnetic field. Then on this side of the magnetic field, you could have this little piece of metal that's going to get pulled over because there's a magnetic field. And over here, you can have its own voltage and its own, load. Might have a big motor over here. And then just by giving voltage to this side, making a magnetic field, this circuit closes. But remember, between these two, there's no interaction. It's isolated. This is just a magnetic field. Okay, so the switch closes by the magnetic field. So you could have like a very small, like 12-volt circuit over here, and this could turn on a very big circuit over here, like 480 volts. So it's good for isolation. It says it's good for crosstalk, and what that is one, the robot over here could turn on, the robot could turn on the magnetic field, and then when this switches, it completes a circuit back into, let's say, a PLC or a second robot. So the robots aren't really wired together. The robots are not wired together. They talk between a magnetic field. Turn on the coil, switch it. So this robot talks to this robot via a magnetic field. Does this make sense to you? That this robot is not directly wired into this robot. We have a relay between them. Robot turns on the relay. Relay talks to the robot. Does this kind of make sense here? Robots are not wired together. They just talk using relays. All right, turning on magnetic fields. Turning on larger voltage with smaller voltages. That's what we talk about. We can have a very small voltage here, making it a magnetic field. This magnetic field doesn't need to be very big to get this relay to switch. I do not have a huge magnetic field in here to get this to pull down. Just a little magnetic field, but the switch over here could turn on a very large load. So that's some of the things that we might use a relay for, okay? And so that's called three-wire control. And there's a lot of different names. We talked about memory, holding, latching, three-wire control. Those were the things that we talked about to indicate this basic holding circuit here, or this memory circuit. And it remembers, I hit start, and so it turns itself on. Okay, that we'll be building up that again as we go. The circuit design is set to contacts are normally open, start. The circuit requires a normally closed stop button. So you need to start and stop, because once you give it memory, once you give this memory by hitting start and letting go, you got a path. It's turned itself on. You have to hit a stop button, normally close, and push it, and that opens to break the voltage, causing that to go off, causing that to open. Then when they go with stop, it will stay off, right? That was the holding. The power circuit and the control circuit are different. So you drew that, and you remember at the top up here, you had 3 wires, and you had a circuit breaker here, and then it went to some contacts here, and that had my overloads here, and that turned on my motor. Okay, that was what you drew at the top. And this was 3-phase. And it can be very high voltage. We use 208, but let's say it's like 480 volts. Very dangerous. So then you pick this off, and you did a transformer here, right? Picking off a transformer, and then this transformer took the voltage and it stepped it down so that we could do our ladder logic, okay? And then let's say this stepped it down to, let's say, 120 volts. So up here, this is all very dangerous, 480 volts. The transformer brings it down to 120 volts. And down here is where we put then our circuit, our control circuit, right? This would be our control relay, and that held like this. So down here is where we had the 120 volt circuit. And once again, they're isolated through a transformer magnetic field. You will learn all about transformers. You're gonna like these. The control circuit has a lower voltage, which is provided by this transformer, okay? The top circuit, the motor, the actual wiring of the motor is very high voltage, 3-phase, all right? We did that power circuit demonstration where I plugged it up for you, and then I turned it on, and then I hooked up a holding circuit. So I did it first. I just hooked this up for you guys, right? And I pushed the contactor to close these with my finger. I just moved it with my finger to shut these, and that motor ran. And then I hooked up this circuit here, and I showed you, start stop memory. And then I just put the two together. So instead of using a control relay, I used a motor starter here. And so these contacts were the motor starter. I melded the two, so when I hit the start button, the motor came on. And we also, for the heck of it, somebody asked, we learned that if you switch any two of these lines, the motor goes in the reverse direction. That's for 131. We're not there yet, okay? The motor starter main contacts closed, which is turning on the circuit. So this is pretty complicated. You'll learn a lot about it. The main thing to know is this is called the power circuit up here because it's three-phase. And this is the control circuit down here, which is lower voltage. And so this motor starter, because this has also got overloads in it, this motor starter has parts of it that are wired into the control. And that motor starter has parts of it that's wired into the power. So my question to you is on a scale of 1 to 10, do you understand there's two different parts of this? The power circuit, high voltage, the control circuit, low voltage. How do you feel about that on a scale of 1 to 10? Doing okay, all right, yeah, I mean, we'll get into it once again in 131, and you're gonna really, really like how it works, all right? Control relays are used for logic, like memory. And then, control relays come in, can be very small, just those little ice cube relays I showed you, and they don't need to pass a lot of current. If you're turning on something big with a relay, because the relay is going to close the three, it's going to close the three and cause it to go. If you're doing that, you need a contactor, because the contactor is a much larger relay with main contacts that are very thick and can handle a lot of current. If you put a lot of current through a little control relay, it's just going to burn it up. This has big pieces of copper that close, all right? And then motor starters were the ones that added all that thermal protection. And those got more complicated wiring because they're wired into parts of the power circuit and parts of the control circuit. So I say that, this is like a Chevy, whatever the Chevy's lowest, a Chevette or whatever. That's like the basic control relay. And then the contactor's got a few more options, like a Buick or I don't know, something nicer. And then the motor starter's like the Cadillac. It's got all the features, all the auxiliary contacts, the motor, the thermal protection, everything like that. So it's just more options as you go up there. All right, so we did CAD. So one way that we did CAD is we had a symbol library. So you were drawing, your ladder logic over here, for example, and over on this side, I had all these symbols created for you. Okay, like you were solenoids, push buttons, whatever relays, and you were just copy and pasting them because the snaps were set up and it just went right in. Or you were just doing insert and you were able to make these drawings by inserting, and then the snaps kind of went in. So basically what I did on the symbol library is I just inserted all the symbols ahead of time for you guys so that they were already there and you just had to copy and paste, versus the other one you had to insert them. So any preferences that you like better? A is the symbol library, and I guess B is where you had to insert yourself off the file. Was there a preference, A or B? What do you guys think, or either one worked? Any preferences, A or B or either? What do you guys think? You like both? All right. You like the file. The file's kind of a copy and paste. I just kind of created it for you. Anything else? So if you were doing the insert, the file, but both will work, all right? Yeah, both work. If you're doing the insert way, there's a program called AutoCAD Electrical, all right? We're just using regular AutoCAD Electrical. So that if you were to insert, that's how that works. You insert the symbols like we did, and it's much more complicated the way it brings in all the characteristics of that push button, everything like that. We're not going to get into that, but that's the procedure that if you get a job someday, it's going to work. Brendan, did you send me your resume or not? I forgot to ask you about that. Or are you putting one together?
I was going to ask you after class, which email do you prefer, the D12 one or the external one?
Either one. You can do hickman@lcc.edu or that they both get forwarded to me.
Okay.
Whatever easiest for you to insert, right?
Yep, sounds good.
Thank you. Yep. Okay. It says review quiz here. I don't have all the quiz questions, but what are the basic parts of a circuit? We have voltage, conductors, a switch, and a load. So, we were talking about voltage, wires or conductors, a switch, and then a load. You guys are learning that a load's using like resistors, but it could be a light or something like that. So voltage, conductors, and load are really the things you need. You really only need voltage, wires, and a load, but it's nice to have a switch on there. What we do is we flatten it and we push button like this, and we might turn on a light like this. So we still have voltage. That's what L1 and L2 are, voltage, and we need conductors and a load, but we like to put a switch on there as well. Okay. It says, what is a multimeter reading? It's not the circuit makes noise. It does make noise, a multimeter does, but it's the circuit is complete. So when we were doing that limit switch and we were like clicking, click, 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 beep, 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 that's what we were doing to figure out how it works. The difference between a momentary and a maintain: a momentary switch has a normal state because it returns. The maintain, you just switch it and there's no normal state on the maintain because it's wherever somebody left it. PB and toggle switch turns on a red light. That'd be something like a push button and a switch turns on a red light, something like that. One toggle switch, one PB. That's an and we also learned about an or when we did and or circuits. All right. And then what is the difference between ladder logic and a rail? So a rung contains symbols and logic. All right. So these are my rails here, my voltage, and all these are my rungs here. This is where the symbols and the logic and everything, usually inputs over here and usually outputs over here, something like that. So that's my ladder logic makeup. Okay. So that's what we were doing for our CAD. I don't think that's the ones that I had there. Okay. So that was a review of the quiz. So we're moving on to fluid power. During this, I've got a few videos that we're going to watch as well. And it's hard to watch videos, so I kind of walk you through them. You have an in-class worksheet that we're going to be going through and filling it out. Okay. So what is fluid power? Fluid power uses fluids under pressure to control and transmit power. Okay, so you pressurize fluids. And hydraulics uses liquid. So when you think about hydraulic fluid pressure, you're really talking about oil. So when you see those big bulldozers out there and those backhoes and everything working in the highway, they're very powerful. They are using hydraulics, all right? And they're got these pumps that are pressurizing hydraulic fluid, all right? And the pressures are very high, up a couple thousand PSI on those hydraulic lines to generate a lot of power. Pneumatics uses gas, compressed gas. Now, air is what we're talking about when we do pneumatics. We're using compressed air, okay? So the thing to remember is that you can really, really compress air. Like if you took all the air in this room right here, you could compress it down into a small can, and the pressure inside of the can would be very high. It would want to like go back out. Air can be compressed. Fluid cannot be compressed. So just by trying to compress fluid, it generates a lot of pressure because you cannot take a bowl of water and smash it down any smaller into a smaller bowl. But you can take a bowl of air and smash that down into a smaller volume of air, and it will go up in pressure. So just by trying to push on fluid makes very high pressures. All right. So we have rotary motion. Okay. A fluid motor produces rotary motion. Okay, called electric motor, fluid motor. The equivalent is an electric motor. So the way an electric motor works is we have a coil of wire here and a coil of wire here, and let's say a coil of wire here. And this wire makes a magnetic field, and this magnetic field is set to be plus, and then this one is minus. And then we got this little stator on here that turns, right? And it makes this minus and this plus. What do you know about magnetic charges that are plus and minus? Do you guys know anything about magnetic charges that are plus and minus when you try and put them together? Right, it attracts. Plus and plus repels. So in this case, what you would do is you would magnetize this coil, and you would make this the minus and this the plus. And therefore, it's going to push this way. And then as it gets going that way, you change the polarity and you make this a minus and this a plus. So as it spins here, it's going to push it some more. And then once again, you keep moving this here. You're going to make this minus and this plus. And then it will push it some more. So you keep changing the magnetic field on these coils to keep pushing and pushing and pushing. That's called an electric motor, all right, and it's using magnetism. We can accomplish round and round or rotary motion using an air motor or a fluid motor. And what you do is you push fluid into here, and you notice that these are veins. These veins move in and out. See how this vein's moving in, this moving in, this moving in, because it runs against the wall. So this area here is larger than this area here. So the fluid will want to, more of it will want to go here, and it will cause this to rotate, all right? And then when it comes through, it then punches out to here, and then this thing starts rotating, round and round and round, because we pump fluid in here and it wants to go around, all right? And that getting circular motion with fluid, either oil or you wouldn't use water for this, but oil or whatever, is called a fluid motor, all right? Fluid cylinders produce linear motion. So we want linear motion, which is not round and round, it's back and forth. We would use a cylinder. The electrical equivalent of that is a solenoid, and that's what we talked about. This was a solenoid right here that we came here and we put a coil of wire here and we gave it voltage. We got a magnetic field. And so if you had a piece of steel here and you had a magnetic field, this steel would move that way. And we let go of it, the magnet would push it back. So you make a magnetic field, it pulls it in. You let go of the magnetic field, the spring pushes it back. But that's how are we getting linear motion using electricity. It's called a solenoid, all right? On a pneumatic system or a hydraulic system, you use a cylinder, okay? And that's what I was talking about, those big cylinders that are out there on all that big heavy equipment that's moving, okay? And so here's the fluid cylinder right here. Fluid goes into the back here, and then it's sealed here, could be a rings or an O-ring or something like that. And so the fluid builds up back here in the pressure, and it pushes this out. And then the fluid has to exit here, all right? And so you can think about it almost like a bike pump is working opposite of that. So if I take a look at a cylinder, here's one right here. So I got air here, or I got a port here, and I got a port here. If I were to put air into here, or oil, but it's the air cylinder, I put air into here, this will start moving out, okay? The more air I put into here, the more this will move. And then when I want to pull it back, I put air into this side, and because there's, a seal in here, the air is going to then push it back this way, all right? And if I were to plug this, by the way, let's say I pull this out, and I'm going to plug this with my finger, and I try and push, it won't push because the air's trapped back here. If I let go of that and push it, it comes out. So it's kind of like a bike pump, except that a bike pump, we're making air right here. We're doing the reverse. We're pushing air in there to cause it to move. So on a scale of 1 to 10, does this cylinder operation seem to make sense to you about how to put air in to get it to move back and forth? How do we feel about that for the cylinder operation? Okay, yeah, so that's what we're doing. We're making, and this is linear movement. This goes back and forth. This is not round and round motion. And this has, a lot of travel. This is like about 6 inches right here. This has a lot of travel back and forth, okay? So that's how that air cylinder works. So there are mathematical relationships to govern the behavior of fluid. So this is a fluid power video. We're going to watch a couple of these, and I'll turn on the captions, and we just got a couple of these, and we'll try and walk you through it to be sure that it makes sense. All right, hang on, let me turn on the closed. Oh, I don't want this. I want closed captioning. Give me closed captioning. Give it to me. Where are you going? Fluid power. All right, so it's on. I'll make it big because this is big, but it's
location to Enosis.
Okay.
In the 1600s, Blaise Pascal.
So is this working for you guys to read the closed captions, or do you want me to kind of narrate as we go? Can you guys read the closed captions? Does that make sense? I hope I can see your responses. Oh, I might not be able to see it. Somebody respond to me. Can you guys read the closed captions? Okay. Okay, okay, I'm gonna let you read the captions and I'll stop once in a while.
Mathematician, a very important contribution in the field of fluid motion. This contribution, known as Pascal's law, relates the transfer of pressure through a fluid.
Okay, Pascal's law is the first one.
Pascal determined that a contained pressurized fluid will exert pressure equally in all directions. Pascal's law states that pressure set up in a confined body of fluid acts equally in all directions and always at right angles to the containing surfaces.
So that's basically, if you compress the air in here, it's not just pushing out the bottom of this thing, it's trying to push out the side walls and everything equally, all right?
Another important problem in mechanics was discovered in the late 1600s by Robert Boyle, an Irish physicist.
Boyle's another important one.
Boyle's law is an experimental gas law which describes how the pressure of a gas increases as the volume of gas decreases.
So here's another thing. If you press down on the fluid and start smashing it, it gets smaller and smaller and smaller, but the pressure starts going up inside of there, all right? And that seems to make, I'm sure you guys.
First statement of Boyle's law is the absolute pressure of a confined body of gas varies inversely as its volume, provided its temperature remains constant.
So
in a physical system,
less volume, more pressure.
As the volume decreases, the pressure increases.
Volume decreases, pressure increases.
Similarly, as the volume increases, the pressure decreases.
Hopefully this makes sense. You've seen it before.
Expressed mathematically as the pressure at state 1 times the volume at state 1 is equal to the pressure at state 2 times the volume at state 2.
Yes.
This is true as long as both the temperature and mass, amount of gas,
hopefully that
remains constant.
Relationship makes sense. We'll do one in a minute.
In the late 1700s, Jacques Charles, a French scientist and mathematician, discovered an important rule regarding gases under pressure. Charles's law, also known as the law of volumes, is an experimental gas law which describes how gases, when heated, its state of a gas is constant and its temperature is raised. The volume will also be raised by the same rate.
So if you heat the gas, it wants to get larger.
True. If the pressure of a gas is constant, also lower.
So you cool a gas, it gets less volume. You heat it, it gets more.
To the volume at state 1.
Okay, so the thing here, let's say you don't do this at home. If you had an aerosol can, like a spray paint can, and it's trapped. The paint is trapped inside of the can. It can't get any bigger. And if you throw it into the fire, what will happen if you throw a paint can into the fire? Anybody? Have you seen it happen before? Boom, that's right. Because it tries to increase in volume, it's going to get pressure's going to go up there because the volumes can't change. It wants to change. And so instead the pressure is going to go up and it will explode and you'll be hurt. So don't throw a paint can on the fire.
At state 2 to the volume. State 2. This law is true as long as the pressure and mass remain constant. In the mid-1700s, Daniel Bernoulli discovered another very powerful rule in the field of fluid mechanics, known as Bernoulli's principle. This rule is related to the
So this is
theory
an interesting
of
one for you.
energy, which states that energy can neither be created or destroyed. In this fluid system, pressure is potential energy and fluid flow is kinetic energy.
So here's flow in a pipe.
Bernoulli's principle states that an increase in the speed of an incompressible fluid occurs simultaneously with a decrease in pressure.
So this is weird.
This is illustrated by
The
the flow.
faster this goes, because it's going to go faster through the smaller pipe here, right? The faster it goes, the less pressure.
When the water's flow is restricted in section B,
it gets restricted, so it's got to move faster,
increases to maintain the same amount of volume,
but lower
of
pressure.
Simultaneously
so it's kind of weird.
Decrease in pressure.
Faster flow is less pressure.
Reaches section C.
Then it slows down again, and pressure picks up. And that's Bernoulli's.
Pressure decreases in section B. The potential energy converts into
Yep.
And decreases the pressure. Section C. The kinetic energy is converted back to potential energy. This is illustrated by the...
Okay. That's a few of the good ones that we're doing there. So that Bernoulli one, I think, is pretty interesting. So it's important for things like flight. So just real quickly, here's how a plane flies. If I just had a wing like this, if I just had a wing that was symmetrical like this, and I had air coming at the wing, well, when the air hits the wing right here, it has to be divided, and then it has to then regroup and meet up again at the end of the wing as it's going through, all right? But if I shape my wing like this, okay, if I shape my wing like that, notice the top of the wing, this line is longer. If I could take this line and stretch it out, you would see that this is longer than this, okay? So when the air hits here and it goes around the wing and it meets up back here and regroups, the air on the top had to make a longer path because it's a longer trip across the top than a straight shot across the bottom. Therefore, this air must be moving faster. The velocity must be faster than here. This must be a small velocity. Does that make sense on an airplane? This is a longer trip. Therefore, this has to be moving faster if they're going to meet up back there, okay? Because it's a shorter trip. And this said that, well, if you move faster, then the pressure is lower, okay? So in here, you have the big pressure, you know, and in here, you have a little pressure, it's lower. So if you have a lot of pressure here pushing up and just a little bit of pressure here pushing down, your net effect is up. That's how an airplane works because of the Bernoulli principle there, by the way, all right? So Pascal's law. If I push down on this, this pushes pressure out in all directions, not just out the bottom. It pushes all over, all right? And it says pressure is equal to force over area. So let me see, do we have something that we have to do here? It says a cylinder has a radius of 2 inches. What is this? So we know that pressure is equal to force over area, all right? So I'm taking this cylinder and it's got a radius of 2 inches. That's my radius, 2 inches. And I'm going to push 1,000 pounds on it right there, 1,000. What pressure gets built in here? Well, it's going to try and blow this can up. All right. So apparently it is area. Let's get the area, and the area is the cross section here, right? So it is going to be area of a circle is pi r squared. Area equals pi r squared. It says this cylinder has a radius of 2 inches. So we got to make this feet. So 2 inches is 2/12 of a foot, or 1/6 of a foot, because this is in pounds. Oh, this is pounds per square inch. Never mind. We're going to keep it in inches. Sorry, my bad. So area is equal to pi r squared, 2 inches squared. Area equals, let me get my phone here, and I can get my calculator going. I can find my calculator. Hang on. It is 3.14159 times 2 squared. 2 times 2 squared is 4. I got area equals 12.56 inches, and it's squared. Okay, because it's square inches. So therefore, pressure equals force, 1,000 pounds, over 12.56 equals, let me do that, 1,000 divided by 12.56, 79.61. That right? Pressure would be pounds per inches squared. All right. So about 80 psi. All right, that's what they're saying. If I push down this, it'd be about 80 psi, pounds per square inch, inside of here. Let's just check that math. Pressure equals force over 1,000 over 12 point. That looks good to me. I think this looks pretty good. So about 80 psi inside of this cylinder is what we're going to get. All right, what pressure is applied. So that's how we talked about the bike pump. We're kind of working backwards here. That if I push down this rod right here, with 1,000 pounds, I would get some pressure inside here, and then it would generate it back out there. All right. What else we got here? Which pressure is generated in the fluid, and that 80 pounds per square inch is pushing out everywhere. It's trying to completely blow up that can. All right. Boyle's law. As volume decreases, pressure increases. That seems to make sense. If you compress it down, all these little molecules of the fluids get closer and closer and closer together, and they want to, just run all over, right? And so this is a cylinder has a volume of 2 liters containing a gas. Is that what we got right here? And so we want pressure 1, volume 1 equals pressure 2, volume 2. So let's doing this one. We got P1, volume 1 equals pressure 2, volume 2. And this is the uncompressed case, and this is the compressed case. All right. So it has a volume of 2 liters of gas is pressurized at 1,000 psi. If the volume is decreased to 1 liter, what is the approximate pressure? So we're taking this. Oops, let me draw a better version of it. We're taking this, and we're gonna press down on it, and we're gonna make it even more. We're gonna smash it down into even a smaller area. All right. So we have pressure 1, which is 1,000 psi. Volume 1, says 2 liters, and then we're gonna smash it down. If the volume is compressed to 1 liter, what is the approximate pressure of the gas? So we took this space and made it from 2 to 1 equals X. So basically, this side needs to equal this side. So 1,000 times 2 liters is 2,000. It's called psi liter, equals 1 liter times X. If I divide by 1 liter, I can cross this out. I can cross this out. I get 2,000 psi. So if I compress it, it does that. What am we getting? Public knows. Man, so okay, I'm getting some stuff on my LCC that something's happening downtown. But anyway, so this makes sense on a scale of 1 to 10 that if you take this space, stay away from downtown. Yeah, I saw it. If you take this space and you make it smaller and you compress it, the pressure inside of here goes up. And then if we make this half as small, the pressure becomes twice as much. Half as small, twice as much. How does this, on a scale of 1 to 10, does that equation make sense to you? Yeah, it's making sense to you guys. Half as much volume, twice as much pressure. And that's the way that, like, our little air pump works here. We take this and we start making the volume. As I turn this gets smaller and smaller and smaller, and the pressure goes up at the end there. Okay, so that is how that one works. Transmission of power. So the force generated on a small area creates pressure that is then applied to a larger area. And this is the main concept of fluid power. And this is like in your car. Over here on your brake pedal, you have a small cylinder that when you push your brake, with a little bit of force on the brake, it pushes down on a small cylinder, okay, to create pressure. That pressure is then applied to a larger cylinder on your brake calipers, creating an incredible amount of force in order to pinch the brake and to stop the car from moving. So how does this one work? Okay, so we've got, and I'll kind of draw it here so you guys can draw it. We've got this thing going here. We had a small one, and it was going to a big one like that, right? So here's one cylinder, and here's the other cylinder, okay? And so we're going to push here. We're going to push here with a force, it says. S1 has an area of 2 square inches. So this right here is 2 inches squared. And we're going to push with 100 pounds, okay? Now remember, I'm giving you 2 square inches, but if I gave you the radius here, you could get the area by area equals pi r squared. But you don't need to run that calculation because I'm giving you the area of 2 square inches, all right? And then this one is much bigger. The area of this is 10 inches squared. So let's see how this works. I got force. So pressure is force over area. So I got force, 100 psi, pounds per square inch, over 2 inches squared. I get 50. This is not psi, this is pounds, sorry. I get pounds over inches squared. I get 50 psi, which is pounds per square inch. So inside of here, I get 50 psi. And remember, that's everywhere in here, 50 psi, 50 psi, because the law says that it pushes out equally everywhere. So inside of here, I got 50 psi. Okay, so by pushing down here, I generate 50. Well, that 50 psi is pushing up on this one right here. And so what do? We can work this formula backwards. We can resolve it for force. And we do it by multiplying this side by A and this side by A. And so if I get area times pressure equals force. Does everybody agree that I can just manipulate this formula by moving the A up here? That makes sense to you? I can move it. How about a yes or no? We understand how I just manipulated that formula? Yeah, just some basic algebra there. Okay. So now I got area times the pressure. This little cylinder made the pressure of 50, and this area is 10. So if I go 10 inches squared times 50 psi, I get 500 pounds. Okay, so if I push with 100 pounds here, I get 500 pounds here. Pushing with 100 pounds here gives me 500 pounds there. Okay, and that's how transmission of fluid power works. You get these big bulldozers and everything like that, and they got a little pump with that creates a little bit that pushes on a small cylinder, and they get, instead of 50 psi in here on those big things, they get like 2,000 psi on those hydraulic units. Okay, on those big backhoes and everything like that, big cranes, and that 2,000 psi gets applied to all those big cylinders that's picking the bucket up and moving the bucket and everything like that, and you get an incredible amount of force, pushing, on the buckets and the plows and everything like that, and then you can move, they move all the dirt and everything like that. So, scale of 1 to 10, does this concept make sense? Small force on small area makes a bigger force on a bigger area. Got a 10? All right. Wonderful. And I don't know if that's just review, if you guys had done that in physics or something in high school or not. Maybe you've already done it. All right. So compressed air, you're going to have compressed air in the shop. When you go in the shop, they use air. They don't have compressed oil like running all over the shop. One thing's oil's just kind of dirty and it burns. You don't want to have in the shop typically hydraulics, big presses and stuff. You have some hydraulics, but just for running air tools and everything like that, you'll have like an air compressor running all over the shop. Who has an air compressor? Does anybody of you guys have an air compressor at home? Or anybody got an air compressor at home? Yeah. Anybody else got an air compressor at home? You might have little ones, maybe ones that just pump the tires of your car up. Those little ones that you just plug in the battery. Yeah. So you got air compressors. If you have an air compressor at home, it might look something like this. And this typically cycles, maybe between 80 and 120 or 90 and 120, 90, 110, somewhere about 100 psi. Your shop air is going to be about 100 psi, and that's good for calculations because 100 is easy to do math with. So that's kind of what's in the tank from a central compressor. So it takes the air from the shop, and then you start compressing it, and you put it in this tank at 100 psi. Anybody touch the top of an air compressor while it's running? You don't get electrocuted, you get burned, because we said when you take air and you compress it, it gets really hot. And that's what's happening here. It's getting hot, and then it gets put in this tank, okay, at pressure, and it's hot. But then it cools a little bit in the tank here, because that's what the tank this does. It cools it, and then the pressure might go down a little bit. If it does, the air compressor would run again. But you're going to have about 100 psi in here, okay? And then it goes and it gets delivered to your pneumatic devices, all right, like cylinders, or if you got air tools at home or stuff like that. So my next question for you is, I got like sprayers where you can pull the button and just spray air. Has anybody ever felt the air coming out of like a spray gun, a compressed spray gun? And is there anything that you noticed about the air coming out of a spray gun, like if you're using air to spray something off? Anybody ever notice anything about that? You guys know what I'm talking about, like a spray gun, like a little spray, like you could have like you spray it and yes, Robert's got it. The air is cold. If you were to like use that spray gun to blow something off, and you put your hand in front of that spray gun, it's got a lot of air coming out. The air is cold because it works the opposite. When you first take this air and you smash it down, it gets really hot. But then when you take that air and you expand it, it becomes really cool. Like you can freeze stuff. You can freeze stuff just by blowing air on it. Feels good on a hot day. That's right. You're hot, blow the compressed air on you, right? But you could freeze stuff by spraying stuff like that as it expands. All right. So there's different types of cylinders. There's single acting cylinders that have a spring that either returns it or a spring that extends it. And they only have one port for air. You put air into one side to move it, to either open it or to close it. And the spring does it the other way. So this is called a spring return cylinder. And if you look here, I only have one port and it's already starting open, all right? And if I compress it here, it's a pretty tough spring. If I compress it, notice it's just coming back all on its own because there's a spring back here that's pushing out here. So this is spring extend. Air, if I put air here, it would retract it, okay? Air would retract it. So this is there's a little hole here that lets the air in. So if I push this like this and I plug this hole, notice it doesn't want to come out. But if I let go of this hole real quick, it comes back out. That's just venting it, all right? But this is a single acting cylinder because it's only got one port and it's spring return, okay? So that's the first kind of cylinder. Single acting cylinders have a spring versus a double acting cylinder, which is what this other one that I was showing you here is that you put air here and it goes out. You put air here and it returns. And so the issue here is that, you know, this spring retract, you know, that's how much force it got. I could not change the amount of spring force in there. It's set. If for some reason I wanted this to push out more, there's nothing I can do about it. The spring determines the force. If I wanted more force on this one, everybody, if I really wanted this to push out, you know, to break something, what would I do? I would just put more pressure back here. The more pressure I put back here, the more force that's going to push out with. Same thing on the retract. If I really don't want this to get hooked on something and I really want to pull it back, I'd put a lot of force on there. This one, I only have control of one side of it. The spring has got control of the other. So it's not quite as flexible, all right? Double acting cylinders have force in both directions. And this is the symbol for it right here, okay? Directional valves. So we control the air going to these cylinders, you know, whether we want air to the front or air to the back with directional valves, okay? These control the flow and are identified by the ways or ports and their positions. And we're going to go over all this, right? The ways to find the valve function with a way or port being either a line connection or exhaust connection, we'll go over it. And positions identify the number of operating positions, all right? So if you take a look at this, I really want you to understand this valve. So we have a little valve spool in here inside of this valve, okay, that moves back and forth linearly, all right? And what's a valve look like? This looks like this is a valve right here. So inside of here, there's a little valve spool that moves back and forth, and it doesn't move very much. It moves like 1/8 of an inch or less. And what it does is in the blue part here, it creates a leak path. So in this case, does the air leak this way or does the air leak? I could take this plug out here and the air would leak this way. It determines where the air leaks, okay? And so this one's activated by a lever, but I could have it activated by electricity. That's what you're going to be doing, is having your valve activated by electricity, okay? To move this little valve spool back and forth to create the leak path. So let's look at this one. Air comes in and it comes in the port. Notice that the leak path is around here. It can get around the valve this way, and therefore it goes into the front of the cylinder. The air gets leaked to the front of the cylinder, and then the cylinder is going to move. And then the air at the back of the cylinder, well, we got to get rid of it. So the air comes out and it gets leaked around here, and it just gets leaked out to, you know, the room. Now, when I push the valve in and I move the valve spool, I've changed the leak path. Look, this is blocked off now. Here, this was open. Everybody see how that was open, and now that's blocked off. So the air, instead of getting leaked around to B, the air gets leaked around to A. And now A goes to the back. So it pushes it out. And what happens to the air that's already in the piston? Well, we got to leak it. We got to leak it out. So it gets leaked out to the exhaust. So this little valve spool moving back and forth creates a leak path to either bring air to the front or the back or the front. Scale of 1 to 10, does this kind of concept make sense of how we're leaking the air one way or the other? Feel good about it? Okay. And you'll learn about this in 131. Here, have you guys done pneumatics yet in 131? Where are you guys at? Who's my 131 people? Have you guys done the pneumatics yet, or is that next week? We did the lecture Monday. Okay. Yep. So you'll be doing the lab using the same equipment that we're doing. All right. So here's the way this works. Boxes are used to indicate the number of valve positions. All right, the number of indicate whether it's a 2 or 3 valve. So you got 2 options: a 2-position valve or a 3-position valve. These are my 2 options because this has 2 boxes. That means 2 positions. This has 3 boxes, so it's got 3 positions. So that's the first thing you need to know on a valve: is it a 2-position or is it a 3-position? I look at this valve right here, and I don't know if you guys can see this or not. Let me try and get a better. Well, that's really hard to see. There's 1 box here and 1 box here. This has 2 boxes on it, okay? And it's a 2-position valve. That's what is going on that one. It's got 2 boxes. That's the first thing, 2 positions. Now, the ports or the ways are the number of times that the line touches the box. Only 1 box though. Don't look at both boxes. Just pick one of the boxes and look at it and see where it's at. So this touches here. Remember, it doesn't matter if there's 2 boxes or 3 boxes. Just look at one of the boxes and count the number of times it touches. So this touches at the top and it touches at the bottom. This is a 2-way valve. Pick a box. It touches 1, it touches 2, it touches 3. That's a 3-way valve. It touches 1, it touches 2, it touches 3, it touches 4. That's a 4-way valve. And 1, 2, 3, 4, 5 is a 5-way valve. So you're just going to look at 1 box. So arrows are used to indicate the flow and direction. So remember, let's take a look at this. We're only looking at 1 box. If we looked at the box on the left, it touches once and it touches twice. But wait a minute. What if I looked at the box to the right? Well, guess what? It touches once, it touches twice. They have to be the same. Over here, look. 1, 2, 3 touches, or 3 ports on the left, and on the right it's 1, 2, 3 ports on the right. Each side of the box has to have the same number of ports. All right. So arrows indicate that the flow goes right through there. T indicates that it's blocked off. Okay. So arrow, it goes through. T, it's blocked off. So in this case, P to B would get an arrow because it leaks through. But P to A, it's blocked. It would get a T. That's a T. That's an arrow. And what's this? This is A to T here, would get an arrow. But B to T, it would be teed off. That's what these are showing. Is this a lot? In this condition, air flows through it, but when we flip it over to the other one, no air flows because it's got teed off. All right. That's how the flow directions are indicated. All right. And so once again, we use electric solenoids that change that position. You give it electricity and it clicks left and right, back and forth. All right. And electric solenoids operate small valves, allowing pressurized air to go into there. So we can use just electricity to move. We can just use electricity to move this back and forth, or we can use fluid piloted, where we just open a little more fluid and the fluid helps us move this back and forth. So fluid piloted is another way to get those solenoid. They use less current. All right. Here's my symbols. That means air pilot. This is just a solenoid. This just means that the solenoid is moving it back and forth. This means air is moving the valve, that little spool back and forth. And this means is a combination of both. You're using electricity and a little bit of air to move that thing back and forth. These are the different ways to get that little valve spool to move. Here we go. Let's do a couple. Ready? 1 box, 2 box. So it's got 2 positions, and I've got whatever you pick. 1, 2. This is a 2-2 valve, is what I'm seeing right here. A 2-2 valve, and it's spring return, and it looks like a plunger. A plunger pushes it this way, and a spring pushes it back. This one right here, 2 boxes. 1, 2. This is also a 2-2 valve. This is a solenoid. You run electricity to that, it pushes it over, and then a spring pushes it back. That's a 2-2 valve. All right. So let's do this one. 1 box, 2 box. I got 2 boxes. 1, 2, 3, 4. This is a 4-2 valve. Okay. And it looks like air piloted. A combination of electricity will push it over, and a spring will push it back. Single coil. And then I got here two boxes, 1 square, 2 squares, 2. 1, 2, 3, 4, 5. This is a 5-2 valve. All right. 2 position. Oh, this is 4-way. This is a 5-way valve. 1, 2, 3, 4. I got 5 ports on this. So it's a 5-way air piloted. It's air piloted. Okay. So that's how you read these. So does the fact that this is a 4-2 valve make sense? 1 box, 2 box, 1, 2, 3, 4 ports. 4-2. That's a 4-2 valve. How do you feel about that? Yes or no? Scale of 1 to 10. Does that make sense? That's a 4-2 valve. Yeah. Anybody else? It's got 2 boxes, so it's a 2 valve, and you just count the number of times it touches. All right. I'm going to give you guys a quick 4 minutes. So go ahead and take a break. Come back at 9:46. Take a couple breaks, a quick break real quick, and then we will get into the very end of this. All right. So I'll stop sharing and see if I missed anything. Go ahead and take a quick break, and then we'll do fluid sim, and we'll be ready to go. See what's going on with campus. There's an emergency. Well, I got a ton of emails and everything from that security alert. Jeez. All right, 1 minute, more minute, we'll go. Yep. All right. We are going to get going again, so I will go back to sharing my screen. And I'll show you a few of these right here. So just before we get going, I just want to be sure everybody's back. You can hear me and you can see my screen. Wonderful. Okay. So we so far studied about cylinders and about valves. Okay. So once again, here's the cylinder, double acting cylinder. If you needed to figure out how much force you could get on here, I don't know if I have a ruler, but you could measure, you know, the diameter here, kind of looking at it and do a calculation pi r squared, you know, put some pressure in the back of here and you could calculate how much force it comes out of here. You could do a little math on this cylinder, figure out, you know, what is this cylinder capable of doing for force, you know, and given a given pressure. And that's based on pi r squared, the bore, that's the diameter. Just another thing is the stroke of this cylinder. That's how far it extends. And some cylinders can have very large strokes. You know, some could be very short. This one's obviously less, and the bore's less too. This doesn't generate as much force as this one. But sometimes you can have cylinders that have very large bores. That's the diameter, and that gives you a lot of force. But they also have very large strokes because you have to push something for a very long distance. All right. So that's some more terminology that we got going there. So now what I'm going to do is I'm going to go to Fluid Sim. And I've got, this is student version. I've got instructions for you of how to download it if you want to download it. We also have this at the school. And this is a 30-minute student demo, and it's on the page. So I pull up student and I go File, New, I can make a new project right here. And I use Fluid Sim here for my diagrams. So the first one, it says, is we want to do a little circuit. So I need compressed air. That's how that works. I'm going to put an air service on here, and I'll put that there. And what this air service is it's a regulator and a gauge and everything. And this is what we've got hang on the wall. And you can just connect these like this. So I now run air to the regulator where you can dial in the pressure and the gauge. You can see it and everything like this. And it wants a single cylinder. So here's a single acting cylinder right here. And it wants a valve, a 3-2 valve. Here's a 3-2 valve, and I'm going to put this here. So once again, is this a 3-2 valve? One box, two boxes. Okay, so it's two. And then I got 1, 2, 3. So yeah, this is a 3-2 valve. It touches, it's got 3 ports and it's got 2 boxes. Okay. And so I go ahead and I run the air to it. I can just run the air to there, and I can run the air to here. Okay, so that's what we got going for our little item here. So I'm going to go ahead and I can play this. So I'll hit play, and it's playing. So when I activate, I can just click right here to activate this. And this is, once again, a solenoid air piloted mechanism that causes this. And you see when I push this, it moves. And that's what I was talking about by the 2 positions. It's either doing this position or this position. In the current position, it runs to a T. So there's no air running through here. It gets teed off. But this position says, hey, when this switches over, the air comes through, the arrow. And if I click this, boom, it moves to the other position. And yeah, the air runs straight through up to the cylinder. When I let go, the spring pushes it back. All right. So I do this so that everybody can kind of see how the leak path is depicted when that valve spool moves over. That changes the way that this thing leaks air. Instead of teed out, it leaks to the cylinder. Does this help, or does this make sense, the way that the air gets leaked to the cylinder on a scale of 1 to 10? How are you feeling about the way that that's working? This I know that fluid sim, I think, helps everybody a little bit, but basically remember, what I'm doing is I'm giving electricity to that valve spool right here, and it's moving inside of here, and it's causing the air to leak to the different ports here, and that's, you know, that's why that's moving. All right, so I got this. So I'm gonna stop playing. Okay, I'll stop. All right, the next one, we wanted let me look at my sheet here. Oh, a 5-2 valve. All right, so I'm gonna take this, I delete it, and I'll take this and I'll delete it. Okay, so now we want a double acting cylinder. So I'm gonna put a double acting cylinder out here, and it wants a 5-2 valve. Here's a 5-2 way solenoid. Yeah, okay, we'll do this one. This fine. Okay, so this time I'm gonna run air to here, and I'm gonna plumb it up like this. There's that one, and there's that one. Okay, so we can look at it. 1 square, 2 squares. So that's definitely 2 positions. 1, 2, 3, 4, 5 ports. It's a 5-2 valve. This has got 5 ports 2 ways. And you can see right now in this position, air is going to be leaking up to the front of the cylinder, causing it to be pushed into the closed position. Okay, so I hit play. That's what's happening. It's just showing air is getting leaked up. Now you can tell look, I'm running air to the middle. So just take a look at this square right here, because this is what is going to, this is the position that's going to get pushed into it. So I'm running air to the middle. So just say, look, you can tell if I run air to the middle, next time it's going to go to the far left port, which is this. So when I activate this, it pushes the air to the back of the cylinder. And like I said, we got to get rid of the old air. So in this case, when this comes back, the old air gets pushed right out here in this number 5 here. This just go out to the atmosphere. But when I activate it, you can see I can't hold it. Oh yeah, the air is getting pushed out to here, the extra air. All right, and like you could make a mistake on your hookup. Watch this. I'm going to delete this, and I'm going to delete this. This isn't. If I accidentally ran, maybe not accidentally, you could run the air to here like this, and you could run the air to here like this. I've switched them. It's hard to say because of the way that is. But now when I run this, oh, it doesn't like it. Oh, it did. Okay, yeah. So in this case, it starts extended because I switched the leads by accident. And when I activate it, it goes back and forth. But that might not be what you want. It just depends on if you want it to start being extended or to start being retracted like that. And then when I play it, it's kind of working like the way that we want it to when I click here. All right. How's this one look? Scale of 1 to 10. Seem to make sense. The 5-2 valve with the extra leak paths. How's this one working for you? Decent? Okay. So now the people who are in 131 are going to do the 2 coil valves, which they got a little dice here. So I delete this. Now we want a 5-3 valve. 5-3 solenoid. I don't know. I'll pull this one here. What's this one? All right. This one looks more complicated. So once again, I'm going to run the air to here. Oh no, my bad. 5-3. Didn't I grab the right one? All right, there we go. Now we're talking. Okay. Run the air to here, the air to here to here, and the air to the middle. Okay, so when I run this, notice the air is ran to a T. So what kind of valve is this? 1, 2 squares, 3 squares. So this is a 3-position valve. And I got 1, 2, 3, 4, 5 ports. Doesn't matter how you count them. 1, 2, 3, 4, 5 ports. Doesn't matter. It's a 5-3 valve. So what this one has is 2 coils. So this coil pulls it this way, and then the string pushes it back to the middle. And then this coil pulls it this way, and the spring pushes it back to the middle. So the coil, one coil brings in this state here, the other coil brings in this state or this condition here, and the spring returns it to the middle. In the middle, everything's teed off, so nothing's flowing there. So when I run this one, if I go this way, it pushes it and it leaks air to the back. Now when I let go of it, notice it didn't retract. Before it retracted because the leak pass pushed the air, but basically this just tees it off. So this is stuck open. How do I get it to retract? I got to push this side and it causes to come back. So this is a more complicated valve called a 5-3, and it's got 2 coils. And like I said, those that are doing 131 will do this. Now, what ours are equipped with, and I'm going to get this out of here, are flow controls. So let me see if I can find a flow control. Here's a one right here, one-way flow control valve. So there's a one-way flow control valve. And I don't know, this is going to really let me put this in like I want. Let me just try and do it. So if I take this air here and I put it to there like that, okay, and then I double click this, it can do my opening level. I'm going to do like just 1%, all right, and click OK. And now let's see what happens when I play it. And I click this. Notice that it goes out really slow, okay? And when I retract, it comes back. I don't have a flow control there, so it comes back. But if I go there, it goes slow because this is limiting the amount of flow that goes through that. That's called a flow control. And so the saying is, when in doubt, you want to meter out, okay? So basically if you want it to go slow, you would meter the flow coming out of it. So if I wanted to slow this down going that way, I would actually maybe have this backwards. Let's see if I can get this hand where you might go there. So I can move this so it looks a little bit better. There. All right, so now I hit play. It's going to go out fast, but when I let go, oh, it's stuck at 1%. Won't even go. Oh, no, it's got a check valve in it. That's why. All right, so these aren't exactly working like what I wanted, like what I want them to do. You would meter the flow in. I'd have to get the quick exhaust valve, but ours have the moral source. Ours have these flow controls on them, and so they're built right in. These flow controls are built right into the connection fitting. So when you get this right here, this has got a flow control in it. So you can turn this. Sometimes you got to pull this out and then turn it, and then this would lock it down. But this right here would control the amount of flow or control the speed of retraction here. So if you get to there, I think the lab wants you to make some adjustments on the flow control in order to do this. All right. So when I get this, let's say this is my circuit. What I like to do is I like to do function print screen. Mine works a little bit different on here to get this. And then remember, I would come to here and go Control V. And then I've got this here. And then I can go to format, crop. I can take this down and then I can even take this file and put it into my AutoCAD template if I want. You know, once I got that is a lot easier to make a print diagram rather than trying to draw all these lines on AutoCAD. So we use these to make your little diagrams for this, okay? So that's, you know, why we're using this fluid sim. And then once again, I can take this and I could just do, you know, copy. And if I went into AutoCAD on the template, I could do paste it. And then on AutoCAD, you know how we got the border with your name and project and everything on it. You could put this right inside of that AutoCAD template and make it like a nice thing that has the project, your name, your date, and everything like that. So that's why we did. But it's only good for half an hour, and it won't let you print. Okay, so that's what the fluid sim is. And there's instructions on the page to download it if you need to. All right. And so those were some of the things that we were talking about. You need a compressor and the regulator, but we have a whole unit here of separators and everything all built together. Okay. And that's what I dragged in here, kind of this air service unit. You'll see it. It's on the wall of the lab. That's where we got our air from. Here's our adjustable flow control. That's what we got. What I put here. This is, yeah, that's checked. This is a check valve, so air can flow this way, and it would go around the ball that's seated in there. But if air tried to go the other way, it can't get in there. It would just push that deeper in there. So it allows the air only to flow one way. Adjustable flow control with bypass. That's what we have going. All right. So it says the start normally open. Do we have this on here? Hang on. Draw the ladder for a holding circuit that will activate a valve. Modify your holding circuit. The start normally will not only create a memory circuit, it turns on a red light and a valve. The valve actuates the cylinder. Okay, so that's what we got going at the very bottom here. So let me do that. So, and I'll draw it on kind of another piece of paper, so you might have to modify. So we said that we wanted to take our circuit and we wanted to do the stop and we wanted to do the start. Okay. And then I said it was going to turn on the control relay. And then, oops, this is contacts. One here. There's my holding circuit, right? So if I give you this, here it's 17 and 18, here it's 1 and 2. So I'm going to give you this, and then, you know, some of these here, you know, this push buttons, right? Normal, you know which ones are open, which ones are closed. On a scale of 1 to 10, can you wire this circuit up to make a memory circuit? How you feel about this on a scale of 1 to 10 to make this, where I hit start, it comes on, and I got to hit stop to turn it off. Think you guys can hook this up? Remember, my advice is to hook this first, and then on the start button here, even though this has leads coming into it, pump 2 more on the top of this for the parallel there to 1 and 2. Then you would have the start here. Now it said that this turns on a light. So what we have is turning on a light. Once again, I'll give you a light. And we need another set of normally open contacts, which are 5 and 6. 5 and 6. So that would turn on the light. And then it said it also turns on a solenoid or a valve. And so we need another set of contacts, and this is 1 CR, and this is 1 CR, to turn on my solenoid, which is the little valve spool in that baby, okay? And the next set would be 5 and 6, 9 and 10. 9 and 10. Okay, so when I hit the start button, these close, and these close. I let go of the start button. This keeps itself on, which means that these are on and these stay on. And so this would cause the solenoid to extend. When I hit stop, it kills this, which kills these, and the solenoid goes off. And if you have a spring return unit, which was maybe a 5.2 here, if you have the spring return unit, when this goes off, the spring pushes it back automatically. So this is what, this could look like. You might probably have a flow control. You would want to have a flow control in there as well. Where did my flow controls go? Where's my flow controls? Didn't I just have them? Hang on. Looking right at it. Oh, right here, yeah. You have another flow control here because they're on both sides. But yeah, when this gets electricity right here, it's going to. When this gets electricity right here, that is going to push the cylinder out. And when I kill the electricity here and that goes off, the spring is going to push it back. All right. So hitting the start would cause the cylinder to extend. Hitting the stop would cause the cylinder to return. This is the electrical schematic that will control this pneumatic diagram, because this right here is the two wires, okay, for that. All right. So hopefully that makes sense. You'll be working through a lab that's going to be using, some machine control devices and the pneumatic training board, and it's kind of a fun little one. So that is what I have for you today. I'm going to stop, and I can answer any questions. Other than that, you should be able to PDF this and get it turned into me, and then you have a quiz that's open. Don't forget to take the quiz. All right. So I'll answer any questions, or you're more than welcome to go and take the quiz and do what you got to do. What do you got?